Yeah. Good evening, everyone, and welcome to the session 8, live session 8 for the course Deep Learning for Computer Vision, conducted by Professor Vinny. So, can someone confirm if I'm audible in the chat? Yeah. If I'm audible, just can you Yeah, thank you. So, in this week, we will be discussing about attention models and, in particular, how attention has been introduced first in RNNs and then how it has been introduced in computer vision tasks like image captioning, visual dialogue systems, and then a little bit about we'll talk about self attention and transformers architecture. So, let's get started. The pattern is the same like every week. We'll discuss first some numericals and then we will discuss a bit of code walkthroughs. So this is the first question for today. It's a simple question based on denoising autoencoder. So given an input data set X, can the encoder of this particular denoising autoencoder learn a many to one mapping from which is as you know autoencoder maps from input to input, right? Input space to input space. So can this encoder learn a many to one mapping? It's a simple true or false question. Yes or no?
Yes.
Yeah. Yes, that's correct. So as you know that denoising autoencoders, basically the idea is that you have the input in a bit of a noisy format. So you have to generate the true input of that particular noisy input. So since you have a bunch of different noisy inputs that are possible, all of them map to one particular true ground truth input. So that is why many to one is possible. Okay, I think this is a simple question. Let's move on. Any doubts? Please stop at any point and unmute and ask, or you can also post it in the chat. Okay, let's talk about a little bit about the context vector which we used before. Even in transformers, we use context vectors when we're talking about image captioning and other situations, right? In BERT type of models. So these are the following four statements which are true related to context vector out of these four statements. Yeah, I think someone answered. Jacinta has answered. Yeah, the correct answer is 2 and 4, B and D. So let's look at every option one after the other. So as you all know, context vector is nothing but context vector is equal to some parameter alpha times your particular hidden state. So alpha is nothing but again the scores of the values which you have. So scores of your ST into ST and HT. The scores can be like cosine similarity or a bunch of different scoring functions which you saw in the lectures. So that is the basic idea about context. It is basically trying to give a weightage. It is trying to identify which particular input to weight more when you're considering a particular output. In simple terms, that is what context vector says. So the first option says this alignment weights, which is nothing but the alpha values, can be negative, but their expected value over the distribution of the hidden states is always positive. This is false. Alpha weights is a output of a softmax or a scoring function, and then alpha weights alpha is always a positive number. It can never be negative. So the first one is false. The second one, if the context vector CT does not consider connections from h underscore k, where k is greater than a particular time step capital T, it may not work as well with those connections. This is true. So if you're not looking at certain future inputs, and then in that case, the particular context vector for those particular future inputs will not work well. While you can argue saying that oh future inputs depends on past inputs, right? So won't that consider the case, won't it be still possible? But no, always future, while it depends on the past, there's some new elements that are coming in the future also. It's not only dependent on the past. So that is why the second option is true, that if you don't consider certain uh, connections after a particular time step in the future, then it won't work well with those connections. So if B is true, then C automatically becomes false. It's the opposite of is the opposite 2 and 3. Then last one says such a mechanism can be made to work for spatio-temporal data such as video. Again, this is true. We like it works for images. You can also make it work for temporal data like videos. So answer is 2 and 4. Any questions or any doubts in these options? Okay, great. So let's move ahead. Now let's talk a little bit about the image captioning and visual dialogue systems. So select which are false in out of these four particular options. Sorry, what option did you say? Shruti, you need to select the false option, not the true options. Okay, I think let's discuss it. So the false options are B, C, D. The only correct statement in this entire four options is the first one. So let's discuss one by one. First one says if you use attention based image captioning techniques, then it helps better explain failure cases compared to its legacy techniques, which is basically only CNN based or RNN based, as the caption gets generated word by word. This is true. If you There were in fact some examples shown by the professor during the lectures where if you took look at every word and if you ask the model where it was paying attention to, it can clearly focus on the image. Okay, this particular word was paying attention to this particular patch of the image. So you can get more and more understanding of what words were wrongly focused at what particular parts of the image, and you can then identify why the particular caption failed. So that is possible with attention based image captioning techniques. Now let's go to option 2. It says the decoder of a visual dialogue system cannot be truly discriminative as it involves computing the max log likelihood of the correct option. So visual dialogue system has encoder and decoder. Decoder can be discriminative or generative. And when you're saying that maximum log likelihood of the correct option, it means that discrimination is possible. In fact, if you take any standard image classification task, right, when you're doing your cross entropy loss and everything, those are nothing but maximizing your log likelihood. So the statement is false because it can be discriminative when you're considering maximum log likelihood of the correct option. So that is how actually your standard image classification tasks also work when you use cross entropy loss. So option 2 is false. Then option 3, I think this is very simple. The range of blue score. Blue score is a metric to evaluate how much your predicted text is in alignment with your ground truth text. It works on an n-gram based model. So, so basically, blue scores ranges from 0 to 1, and 0 is when there is no correct matching between the predicted and the ground truth. 1 is when there is complete matching. So the actual range of blue score is 0 to 1. It is not 1 to e. Then fourth one says transformers are parallelizable architectures in a sense that multiple models with the same architecture and weights can be run parallelly on multiple devices, whereas RNNs cannot be. So this is a bit of a tricky question option because transformers advantage over RNNs is because transformers are parallelizable. That is true. But the way here it is defined that this particular parallelizability is because of models with same architectures and weights can run parallelly. That is wrong. Transformers are parallelizable because at every point, every token can look at every other token in the input sequence. Whereas for RNNs, you have that hidden state concept, right? You have to go sequentially. Whereas for transformers architecture, each token or each word can look at every other token in the entire input statement when you're processing that token. So that is where the parallelization comes from, not because
Sorry to interrupt you, but this is not the example of parallelization.
that is.
I think the example of parallelization is the encoder parallelization, not the word-to-word mapping or the key value watching is the parallelization.
No, what is encoder parallelism? That is what. So when you're in transformer, there's encoder and decoder, right? When you're encoding the values, you're calculating the query key and value vectors, right? At that particular point, when you're calculating query or key vectors, you're looking at for each token, you're looking at every other token. That's how you calculate query key and value, right? The entire matrix multiplication. So that is where the parallelization comes from.
But how parallelization works in searching the key of query of one word with keys of other word? How parallelization works?
So if you remember the architecture, we'll also discuss the architecture during the code in detail. But what does the architecture says? You first have q, k, v values for each token or each input word, and then what do you calculate? You calculate the softmax between query and first the dot product between query and key divided with some constant d. Calculate the softmax and then multiply it with value. So when you're doing dot product of each value, each word with every other word in your input words. Is that clear?
It's not clear. Because yeah, I can understand that this is a searching or attention mechanism for key value pairs. How parallelization plays a role in this? I can't understand this.
So what do you mean by parallelization? Firstly, I think your definition of parallelization is not clear. So what does RNNs do? RNNs take every word in a sequential manner. They process it in a hidden state, and that hidden state is sent to the next time step where you again process a second model. So it's a sequential manner that you understand in RNNs. Uh,
Yes, yes, yes.
Yes, that is clear, right? So here we are not, when you in RNNs for a time step t is equals to 1, we are not looking at the values which was, let's say time step t is equals to stage 9. You're not looking at values from time step t is equals to 1 and 0 when you're processing t is equals to 1. You're only taking the hidden state input. You're not looking at the actual token from t is equals to 0 or 1, right? In RNNs?
So you are saying that all attention-based models are parallelized model?
Not all attention based. So there are attentions which have been defined in your normal systems, normal as in like before the transformers. Transformers is complete attention based systems, but it's not necessary that all attentions have to be parallelized. You can also put a mask and make sure that they're not parallelizable. But a vanilla type of an attention is definitely parallelized. It basically looks at every other token when you're processing one particular token.
Okay, except mask-based attention, all
Yes.
attention-based models are parallelized.
Yes, yes. If you're looking at everything when you're processing one particular word in the input, it means it is parallelized, right?
Okay, okay. Thank
Yeah.
you.
So yeah, that is why statement 4 is false because the parallelization definition is wrong here. Okay. The false statements are 2, 3, and 4. So let's go to question 4. Now this is based on the transformers architecture itself. So just pick the statements which are true out of these four options.
Second, B is the answer.
B you're saying, right? Okay. Let's just wait for everyone else. I'll one more minute and then we can discuss. Yeah. So the correct answer for this particular question is C, not B. So let's look at the options one by one. So the first option says vision transformers do not require positional encoding as they are not temporal data. This is not true. This is false. In fact, you can give a positional encoding because if you remember vision transformers, they do it in patches. So each particular patch belongs to a particular row and column index, right? You can give some type of positional encoding in that way. So first statement is false. Second statement says input data is parallelly passed to all the stack encoders in a transformer. This is wrong. In fact, input data is passed one encoder after the other. Like there are n encoders in a transformer. Your input data is first passed to the encoder 1. The output of that is passed to encoder 2 and so up to the last encoder. So statement 2 is false. Statement 3 says input data is parallelly passed to all the stacked decoders from the last stacked encoder. This is true because if you look at the architecture itself, the last encoder will be sending its output to every decoder that is present in the transformer model. So option 3 is the architecture of the transformer itself. So option 3 is true. Option 4 says the weight values in each of the QKV matrices of the multiple heads of the first encoder are kept exactly the same, but the inputs to the matrices are kept varied. This is wrong. In fact, weight values have to change. That is when you get different QKV values. If weight values are the same, then all the Q is equals to K is equals to V. Then there is no point of doing your self attention and all those things. So option 4 is wrong. So that is why option 3 is the correct option. All the other options are the wrong options. Any doubts or anything that is unclear?
Yeah, this is clear, but I have read somewhere that vision transformer have only encoder architecture. Decoders are not present in vision transformer. Is this the true statement?
No, no, not necessary. So again, there are different types of architectures. Some are called generative architectures. Some are called as decoder type of architectures. In your encoder type or generative architectures, you just use the encoder for generative tasks, where you keep on generating bunch of different images or your other type of generative computer vision tasks. Whereas you have encoder and decoder for your normal decoder, like image captioning task or type of simple classification. So based on your case, you can have both encoders and decoders.
No, I am talking about the only VT type of architecture, vision transformer type of architecture.
Yeah, that's what I'm saying. So in vision type of an architecture, so if you're doing for a simple classification, you can use only the encoder part of VIT, and then you can have simple linear layers after that to do the classification. It depends on your task, is what I'm saying. It's not necessary that vision transformers are only encoder architectures. So then let's look at a little bit of a numerical based on the transformers architecture, especially the self-attention mechanism. So I'll give you 2 minutes time. Just read this question and select the correct option. It's a bit of a lengthy question. So I hope the question is clear. All you have to do over here is the q and k values elements in that matrices. We are multiplying with some scalars x and y. So how is that x and y impacting on the softmax output? That is the question. Is it making the softmax more closer to uniform or farther away from the uniform, or is there no change? That is what your question is. Okay, I think let's discuss this question once. So the correct options are basically up is basically when they are going beyond normal uniform distributions. 3 is going closer to the uniform distribution. 4 is no change. 5 is again going away from uniform distribution. So first let's look at the question. So like I said, all we are asked to do is what if these elements in Q matrix and K matrix are multiplied with some scalars x and y correspondingly. Now how will that affect the softmax value? So if all elements of q is multiplied with x, you can bring x outside. Similarly, if all the elements of k are multiplied with y, you can bring y outside. So now you're left with softmax of x into y and the normal q k transpose divided by square root of this dk. Now you have to look at what are these x and y and how does it affect. So if x and y is less than 1, let me just write it down. So if x and y is less than 1, so what it means, then you're multiplying this softmax value of qk transpose, right? You're multiplying that, you're multiplying the value of qk transpose with something which is less than 1. Then it makes all the elements in that particular multiplication closer to each other. So if all the elements are closer to each other, then it is closer to a uniform distribution. Whereas if x and y is greater than 1, then when you multiply it with this qk transpose, then you make the elements in this output qk transpose far away from each other. Then the more far away they each other, the output of softmax will be further away from uniform distribution. like not close to uniform distribution. Whereas if x into y is equals to 1, then it doesn't matter. It will give you the same output, whatever was there. So I hope this reasoning is clear. Any doubt in this reasoning? If you understand the reasoning, I think it's just identifying which case all your options fall into. You just have to multiply x and y values and check whether they're greater than 1 or less than 1 or equal to 1. Any doubt in this idea about how xy is less than 1 is making it closer to uniform distribution? Okay. Yeah. Is there a question?
No.
Okay. Okay, then let's move ahead for the final numerical, and then we can go to the code. So this is based on the positional encoding of your attention transformers paper. Attention is all you need. So you are given a particular position encoding mechanism P of ij. So you need to find the condition when P of I comma 2j is equals to P of m comma 2n. So I hope you guys remember P of ij function is nothing but is a sinusoidal function. That's what is used in attention is all you need. So just follow that sinusoidal function and identify when was that sine of I comma 2j is equals to sine of m comma 2n. So you'll get a condition and identify which of these conditions in the options will satisfy it.
How to calculate this?
So I hope you remember the formula for the positional encoding. Is that clear? Is that
Yeah,
Yes.
we have to calculate the similarity score, no?
No, not similarity score. So this is the positional encoding formula. So P of I comma 2j is equals to sine of I divided by 1000. Yeah. You just have to equate them. I think now I anyway show the answer. We can just discuss the answer itself. So we have to just equate the two values. P of I comma 2j is equals to P of m comma 2n. So sine of that, when is sine of x and y equal? When either x is equals to y or mod of y minus x is equals to 2k divided by pi. 2k pi, sorry. But since we are having all rational values, arguments x and y are rational, so the only scenario that is possible is if x is equals to y. And then it means that I of I divided by 1000 to the power 2j divided by d model is equals to m divided by 1000 to the power 2n by d model. It again further, if you simplify, this is the equation. Just identify which conditions out of these four will satisfy this equation in the bottom. The answers are A and B. Maybe you can try it out in your own time after this session. But yeah, do let me know if you have any questions in the further simplification of this equation to these conditions.
Okay, I just want to know, like, this, actually, what is the purpose of this question? We are equating sine, sorry, I might have missed few concepts here. No, like, why we are trying to equate? What is the purpose of this kind of question?
Okay. Purpose, maybe, do you understand the concept of positional encoding?
Yes, key
Yeah.
speed is, yeah.
Yeah, positional encoding basically makes sure that it keeps a track of what position each word is in the input state in a rough way. That is what positional encoding does.
Mhm.
So in this question, we are just trying to identify, is there any scenario where these particular conditions can be true? So this is basically testing your knowledge about your positional encoding functions. Do you remember that functions and how it works? That's it.
Okay.
Yeah.
So
So
it is checking in a sequence if there are any similar tokens are there.
in a way, you can think about similar position and embeddings of the tokens, not just the similar tokens.
Similar embeddings.
Positional embeddings, yeah. Because again, embeddings means are different things. Positional embeddings are different from just embeddings.
Okay, it has the position information also.
Yes, yes.
Okay, got it. Thank you.
Any other questions in any of the 6 problems which we discussed? Okay, then if there are no questions, let's go to the code. So today's code is entirely based on writing the self transformers architecture from scratch.
Sorry to interrupt you. I have a question.
Yeah.
In the previous lecture, we have used RNN based model can you please tell that every RNN use every hidden layer of previous layer to next layer, or some hidden layer are not used?
No, RNNs do it in a sequential manner, right? So
Yeah.
h of t is dependent only on h of t minus 1. It is not dependent of h of t
It's
minus 2
always
directly. Yeah, it doesn't depend on h of t minus 2 directly. Because h of t minus 1 indirectly again depends on h of t minus 2.
And if we talk about the first layer, first H node,
Right,
then
right.
H node depends on which
It
value.
doesn't depend on anything. That's why if you remember, we initialize with zeros, right?
Then what is the dimensions of H node?
No, you have the same dimension as your hidden state dimension, but you initialize those values with zeros. Just saying that key that is the inputs like this is a starting token of your input. So that is why it's not dependent on anything.
Yeah, starting token, but what are the dimensions of that starting token?
So
Same as input?
no, hidden state dimensions are different from input dimensions.
No,
So
I am
what
talking about H node. H node is the hidden dimensions for first input.
exactly
Okay.
that will also be the same dimension as your other hidden states, right? Every hidden state has the same dimension.
Okay. Every hidden state has the same dimension. Okay.
Yeah.
Okay.
Okay, so in today's code, it's entirely based on trying to write from scratch the transformers architecture. So we'll go in detail about how the architecture itself works, and then what are the outputs of these architecture, the matrix shapes and everything, and how to write it. So do pause me at any point. There's a little bit mix of theory and the code in this particular code walkthrough. So as you all know, this is what is architecture transformers architecture look like. On the left side top, you see your encoder part of your transformer architecture. So you're given a particular input, and this particular input is now first gone through some tokenization and embedding. So there are standard embeddings available in your PyTorch and PyTorch, or if you're using TensorFlow or Hugging Face, all of them have some standard embeddings available with them or tokenization. So you first convert your text into vectors with the help of these embeddings. Then you send it to the you append it or add it to the positional encoding. We look at what positional encoding looks like in terms of code. But the function is nothing but what you saw, the sign when it's even, its cost when it's odd. So positional encoding adds with your embeddings, and then you send it to the encoder layer. So encoder layer, again, each encoder layer consists of two different things. One is your multi-head attention, and then another linear layer. And each of these particular layers are followed by a normalization and residual connection. So this is a typical encoder layer. Like this, there are n such encoder layers. And now the output of this particular encoder, you send it to the decoder layers, all the decoder layers. Similarly, at the decoder, you will also send the output, but here you use mask attention because you don't want to predict or you don't want to see when calculating the attention the future tokens which have not been predicted yet. So that is why you do a masked multi attention. We'll again discuss how to create those masks and everything in the code. And then you keep on calculating n such decoder values and you finally predict a probability. So you can use your simple softmax, cross entropy loss on over here, or any type of loss depending on your particular application. And operation wise, these are the for self attention because all of them are based on self attention. There is no RNNs concept. That is what transformers entire novelty is. Entirely everything is based on self attention, which again, if you have multiple of them, it becomes multi-head attention. Self attention works on these principles, which you see on the bottom. You have your input values. Let's say we have four values, x1, x2, x3, x4. You multiply each of them with their corresponding weight values, weight matrices, wq, wk, wv to get the outputs qkv. So now these qkv is used to calculate attention values. What is the function? You first calculate softmax, first calculate dot product between q and k transpose divided with the root of dk. Dk is the dimension, and then you take the softmax of this entire value, and then you multiply it with the matrix V. So this is a simple output of a self-attention. Now this is repeated 8 times to, 8 is a standard value for transformers. It's not just necessary 8. It's repeated some k number of times, and that will become your multi-rate attention output. So now let's look at it in a bit more detail. So this is a simple template. If you don't want to know what are these encoder decoders, you can just look at them at like a black box. You give your input in, let's say my task is machine translation. You give your input in, I think this is French. You give your input in French. It encodes using all your multi-rate attentions. Then that last encoder value is sent to the decoders, and then you decode your output. You convert it into English language. I am a student. Now let's open it up a little bit and see. Like I said, there are n number of layers in each of these encoder blocks. So in this particular scenario, you have six number of encoders. So your input first sent to the first encoder, and in a sequential way, you send it to all the encoders to the top. The output is then sent to all the decoders, and finally, the last layer of the last decoder layer outputs your whatever output you have. I am a student.
Yeah, this is the same as you have asked the question.
Exactly. Yeah.
Okay, now I have rejected that answer because the same input that we have entered in the initial phase of encoder is not passed to the decoder, but the input of decoder, input of encoder is passed to all the decoder. Okay.
Output of the encoder
Yeah,
is passed.
yeah. Output of encoder is passed to the all the encoder.
Yes,
That is not the same input that we have passed.
no, if you look at the statement, no, let's look at the statement again. So input data is parallelly passed to all the stacked decoders from the last stacked encoder. You have to come read the entire statement, right? The entire statement says that input data is going to decoders from the last stacked encoder. So it means it has gone through all the stacked encoders.
Okay.
Yeah. Okay. Then let's look at the architecture in terms of the values which we previously discussed, or the blocks which we previously discussed, the same blocks: input embeddings, multi-rate attention, and feed forward network. Then that goes to decoder. In decoder, you have two different multi-rate attentions along with masked multi-rate attention. We will discuss what those are. Okay. As usual, you first have to import all your necessary libraries. In our case, again, we're using.
I have a question in the above architecture.
Yes.
We have used a feed forward network in the encoder. But
Yes.
Before encoding, we have passed the positional argument or positional embedding.
Okay.
So when we pass these architecture to a feed forward network, then is there any impact on the positional embedding, or positional embedding is intact?
So, positional embedding is done much before even you start with your encoder.
Yeah.
So, yeah, so each encoder, before going to feed forward, you first calculate your attention values. Those output will be sent to the feed forward.
Yeah,
So,
yeah. Those output is
the
sent to the feed
no,
forward. But when we pass these to feed forward, we are vanishing the positional encoding.
yeah, because you're already calculating the attention before that, right?
What is the benefit of positional encoding?
Because for calculating the attention, right? When you're calculating attention, you need to know where your particular position is for each of the input values. That's how.
After attention, we are vanishing the positions.
See, it's not vanishing, it's called encoding, right? So okay, let's think about in terms of convolution neural networks. So what did we observe from convolution neural networks? The first layer, if you look at the activations, it looks at small edges and all. The second layer creates complicated embeddings based on these simple edges, like textures or more curvatures and all those things.
You are right.
Exactly. Same concept applied over here also. Initially, the first layers takes that position embedding, creates an encoding or representation with the help of attentions. Now those are further refined with the help of feed forward.
Okay.
It's not vanished anywhere. It's all in a compositionality basically.
Okay.
And yeah, let's go ahead then.
Just one question there. What is this NX in the encoder? I can see in the leftmost side this symbol NX. It is number of encoders.
Number of encoders. Basically, this is one encoder block. Like that, you'll have n different encoder blocks.
So how to decide how many encoders we will need?
So that is a hyperparameter that you have to tune for your particular data set. So there is no standard numbers. You can start off with what transformer or paper suggests, but depending on your particular application and data set, you'll have to play around with it. So yeah, I think I won't go through again all these libraries. By now, everyone must be aware of each of the importance of each of these libraries. We've discussed it. Let's go ahead with the first component, which is your word embeddings. Like I said, there is something called as nn.embeddings available in PyTorch. In Hugging Face also there are some embeddings. So what are these embeddings? Basically, you each text for humans, we know that this is word, this like each sentence, right? In this sentence, each of them is a word. We can separate these words, but for machines, there's no concept of words. It's all numbers for them. So to represent or to project these particular text into some numbers, we use something called as embeddings. So the simplest embedding which we saw in the last class for RNNs was each particular character we gave a number 0, 1, 2, 3, like that we created, right? That is a very simple type of embedding. But obviously those type of embeddings won't work when you have big data sets. So in that case, you have to create, so you don't have to train anything. There are existing trained embedding vectors which are available. They have been trained on a bunch of different data, like a billion, not billion, I think a very huge data set. They were trained to identify which particular word or subword can be represented better in a subspace. So those all training has been done. You can just use those particular trained vectors or trained models. And what does the model do? It takes in a word, particular word as the input, and it outputs a vector of 512 dimensions. So that is what you get. So if let's say let's look at the last line. If you have a batch size of 32 and a sequence length of 10, which is basically your sentence has 10 words, then the output will be 32 into 10 into 512. So for each particular word in that particular sequence, there will be 512 dimension vector. And like that, there are 10 words. And in total, you have 32 batch size, like 32 samples in that particular batch. So that is why this will be the output of your embedding. So let's
Which architecture this embedding depends? Either word to vec or
yeah, so you can pick any of the standard architectures. For now, we picked which are available in PyTorch and embeddings. I'm not sure which is trained, which model did they use to train this. You can look into the documentation.
okay.
Yeah, you can use any embeddings that is standard. That is not even nowadays LLMs. All of them come with their own tokenizers and embeddings. So each model you can look at those also. Okay, so how to create first your embedding? You have to create a small class embedding saying it's a neural network class. That's what you inherit the nn.new module. And then, like every other neural network class, you'll have two important functions that you have to define: init function and forward function. Since in our case, it's a very yeah. Is there a question?
Yeah. So this embedding, have we selected only the text-based embedding, or we can go for image-based embeddings also?
You can go for image, but for now we are just doing text. We are keeping the task simple. It's a simple text-based task. We're not doing image, right?
Okay, good.
So yeah, like for every other neural network class, you have two different functions that you have to define: init function and forward function. In your init function, you just, in our case, it's in this particular class, it's very simple. You just have to create a global variable, which is calling the nn.embedding. Mention what is your vocabulary size and embedding dimension, which is 512, and I think vocabulary size, I think it was 10 or something. We'll just confirm once when you give the input. And then after you define that particular global variable, next in the next function, define forward function, you need to show how the data flows when someone calls this class. How the data flows in our case, it's simple. You just take the input x, process it to the self.embed, which is the global variable for embedding. You get your output, which is a vector of 512 for each particular word, and that is your output statement. That is your output variable. That's it. It's a simple class. We don't have to do any more data this particular architecture. So now let's move ahead and let's talk about the positional encoding itself. So like I said, what does the positional encoding do? It does two things, like it's mentioned on the screen. What does the word mean, and what is the position of the word in the sentence? So let's look at the positional encodings which was used in attention is all you need paper. So they said that in an every event time step, you can use the sign of this particular function, sign of position divided by 1000 to the power 2i divided by dimension, embed dimension. And every odd step, you use a cosine function. So there is a bit of a math as such. You can see in the links, I'll share the links with you at the end of this slide. You can look at a very good visualization which will help you understand what exactly is position embeddings. In a very crude sense, it is the position of the word in the sentence, but why sine on cos? So there is a very good theory behind it. And again, these are not the only possible functions. There is a lot of different functions that are coming up, which people have used also, apart from these simple sine and cos. But these are very standard. You can use blindly sine and cos. Okay.
Can we infer anything if I want to compare these mathematical equations with respect to RNNs? So can I do that kind of a comparison and understanding?
So, with RNNs, how do you want to compare? In what sense?
So how RNN functions and how transformers functions if I want to differentiate in these models.
So, basic differentiation is the way they process each of the input word. So, like I previously said, RNNs process it in a sequential fashion. It means that when I'm calculating a particular at time step 3, if I'm calculating the hidden state value, I'm only looking at or depending at the previous time step. I'm depending on that, right? Whereas for transformers, at every word, I don't have to depend on anything because I can take the entire input word. I'm using entire input, all the words to process the attention value for each particular word. So that is the benefit of transformers compared to RNNs, because then I can easily parallelize these particular operations across multiple threads of GPU, because I don't have to wait for any previous token or hidden state value. Whereas RNNs couldn't do that. That is the major difference between RNNs and transformers. But in terms of positional encodings, I don't think, because you can compare, because RNNs don't have anything like positional encodings, right?
Okay, got it. So these formulas is only for these positional encodings. Okay, got it.
Yes, these formulas are only for positional encodings. Okay, so there are two variables in this function. What is the first variable? POS. We define POS to POS is nothing but refers to the order in the sentence. I refers to the position along the embedding vector dimension. So let's look at the vector matrices itself. So your first input word is gone through the embedding vector, which we saw in the previous class. What is the output of the embedding vector? You have your input words on the row dimension. On the column dimension, you have your embedding vector. And now, if you look at the positional matrix, position encoding matrix, on the row, you have your position of each word. And along the column, you have I value, which is along the particular embedding matrix. What is this? What is the position along the embedding vector matrix? I represents that. So you just add these two and nothing else. So let's look at how do you even create. You just use that function which we previously saw, and you just generate from a bunch of values from this particular range. So if you look at it, you simply write a multiple for loop function. Again, here also you need to create a class. So all the blocks which we defined today, so we'll define a bunch of different blocks. All of them are created as a neural network class, because all of them will have a particular init function and a forward function, and all of them keep on building on top of each other, and finally you create a transformer architecture. So that is standard. So even if I miss sometimes in between mentioning that's a neural network class, most likely it's a neural network class. Just look at the class definition and you'll be able to identify it. So in positional embedding, in the init function, all you have to do is basically define those two functions. And what's the best way to define? You write these functions itself, like math.sign position divided by 1000 to the power 2i divided by the self dot embedding dimension. I think embedding dimension is 512 in our case. So I value is basically coming in this for loop, and position values are coming from the outermost for loop. So like I said, position value depends on the number of words row wise, right? The position variable, POS variable, it's number of words that row, and whereas I is the vector dimension, self embedding dimension. And then we see that for the even time step, this is the sine value. For the odd time step, we use the same formula, but we use a cosine value. A small difference here, we use I plus instead of I because it's a odd time step. So once you define that positional embedding PE, you just use it in the forward function. So you add that x plus torch autograd variable PE. So this is a particular type of variable which PyTorch, like if you simply write Python variables, you don't have to write variable, right? So PyTorch, there are certain what do you say, certain types of variables which you can create as autograd variable, which will take in values when you're processing it during runtime, and also if you want to calculate the gradients and all, you can mention it with the help of that particular autograd variable. Like requires grad false because you don't have to calculate any gradient for this particular variable, but you get the value for this during runtime. So that's why you define it as a variable, PyTorch variable. So that's it. You just add them. X is equal to x plus this self dot position. It's as simple as that. Nothing much to do. So now let's look at the self attention function itself. Okay, so let's look step by step. What is the first step? First step is to calculating the self attention. We need to create three vectors, right? The query vector, key vector, and value vector. In our case, we create matrices with the help of the weight matrices. So each of them will be of the dimension 1, 64. Vectors will be of the dimension 1, 64. Matrix will appropriately be different. And in multi-head attention, like I said, we use 8 self-attention heads.
From where this one multiplied by 64 comes?
No, we'll calculate it. I'll show you how we calculate. It will be multiplied with the weight vector, and that weight is what will be learned during the training time. So that weights is what is finally optimized during the transformer training.
Yeah, the value of weights we will calculate during the training. But the size of 1 cross 64, from where this size comes?
So that's again a hyperparameter which you have to pick. So even like 8, right? Why 8 self-attention heads? So these are transformer has a bunch of different hyperparameter values like these. So 64, 8. So you have to fix your values and keep on training it. So you can.
I am asking this question because we are passing a fixed input. The input have a fixed dimensions. So is this 1 cross 64 depends on the dimensions of input, or it's a hyperparameter user can give as per his convenience?
Just wait for 1 minute. I'll show you the calculations. There is a lot of calculations in the next steps, which will help you understand how is that 64.
Okay.
Yeah. Okay. So in the second, where was I? 8 attention self-attention heads we will be calculating for each of multi-head attention. And let's look at the second step where we'll be calculating the score with the help of QKT values, the softmax of those QKT values. And then you divide it with your dimension vector, that is step 3. Step 4, we'll multiply it with a value vector, and step 5 will pass it to a linear layer. Now, here let's look at the dimensions which you are asking about. Okay, so your input vector, okay, so after the embedding and the positional encoding of our output, we will resize it to 32 cross 10 cross 8 cross 16. So again, after this resizing value is initially from embedding 512, you're resizing it to 32 cross 10 cross 8 cross 16. Now these values will be multiplied with certain weight vectors, which will convert to 64. Now those weight vectors size and all, which will be compatible to get the 64. So 64 is a hyperparameter which you're getting after multiplying with the weights. So if you can ask the same question like why 8 comma 16, right? So 8 here because we are dividing it to 8 attention heads, and 16 is the other hyperparameter which will be compatible with your number of values in your input. So I hope that is clear.
No, still not clear.
So 64 is 64.
Can we go above?
Yeah, sure.
We have taken a dimensions for input.
Okay. Yeah, we took the dimensions 32 cross 10 cross 512.
512.
Yes.
Now how we reduce these dimensions first to 1 cross 64 so that we can pass this 1 cross 64.
No, we are not one second. We are not reducing to 1 cross 64. That this is 1 cross 64 is a one for one particular word. You can say you have an entire matrix. It's not 1 cross 64 vector. So the actual size will be this. Actual size will be 32 cross 8 cross 10 cross 64.
Yeah, this is the complete matrix
Exactly.
size. I
Exactly.
can understand.
Yes.
But still I am not able to understand that from where this 1 cross 64 comes. Can I use 1 cross 32 or can I use 1 cross 6?
Yeah, you can use. You can use. It's just a dependence, right? How much big of a vector you're creating.
But weight is the either key or value or query. All are weights. Are the multiplier of input matrix. Okay. After positional or any word embedding. Okay. Then if I selected as per my convenience, then it may impact on the metric multiplication. Then I have
Yes.
then I have to choose this quotiently so that metric multiplication may happen exactly.
Okay.
So
I think I get your point. Just 1 second, just hold on. So just use this formula. Self dot embed dimensions, which is your 512 divided by number of heads. That you'll get your 64.
okay.
Okay. Yeah, you can. There's a ratio again. You can. Your next question will be, how is this fixed, right? Why 512 and 5 8? That again you fix it in certain way, but the ratio should be certain. Your ratio is what your output will be.
Okay.
Okay. Yeah. So we create those with. I think I lost the track. Oh, 1 second. Sorry. Yeah. Step 2 is basically Q into K transpose. Then divide by D. Then you multiply with your value vector, and then you send it to your linear layer. Now let's look at the calculations itself step by step. So first you in your init variable, you create all your global values. First you create your embedding dimensions, which is 512. Then you create number of heads, which is 8. Then you calculate the head dimension for each particular, which is in this formula, embed by heads, which is 64. Then you calculate the query matrix, which is a linear layer between this query matrix is coming by multiplying with the weights, right? So that is why we have a linear layer. And what is the dimensions? Input dimensions is 8, output dimensions is also 8. So single key matrix for all the 8 keys that will be generated. Same key matrix and value matrix. These are weight matrices. These are not the query key value vectors. These are matrices which will be of the shape 512 comma 5. No, it will be single head dimension, right? So 64 comma 64 basically these key weight matrices dimension. Similarly, you have your output variable, which basically is the output matrix which will be multiplied to get your output attention of the output. So all these, if you look at the diagram, don't know if you have the diagram here. Okay, so let's look at here only. So QKV values, after you calculate the output Z values, and now all these Z's for all the 8 attention heads will be combined, and again they will be multiplied with another weight matrix to give your final output. So that is your that weight matrix which is multiplying with your combined Z, that is your self dot out. So this is another variable, and now let's define it in the forward function. So in the forward function, you first define few variables which you'll be needing, like batch size and sequence length.
Sorry, this weight vector is calculated for all the 3, right? Key query values.
No. So there are 4 different weights totally. One weight is query, one weight is key, one weight is value. That is okay. The fourth is output. This output is coming after calculating the softmax and Z. Do you remember the softmax equation, right? And after calculating the softmax, you get Z value for each of the self attention head. Now you combine all of those Z values into one big matrix, and then you project it into a lower dimension, which will be your final output. And that projection is done with the self dot out weight.
Okay, so basically this is the encoded values. or the particular
No, this is just the output of the multi-head attention, because it's not yet the entire encoder block, because we'll have to do normalization, residual connection, and linear layer. All of them are still remaining. This is just multi-head attention output.
okay, initial step. Okay, got it.
Yeah, so let's go back to the architecture. So it's just the output of this multi-head attention, nothing else. Not even normalization, just this output.
Okay.
Yeah,
I have a question.
yeah.
I have read all the transformers, but still I have not understand the importance of value vector.
Okay.
Yeah.
Let's.
Key I understand. Queries for which we are seeing, and keys are to whom we are seeing, and what is the importance of value?
Okay, let's think about it this way. Everyone uses Google search, right? Now you enter a query in your Google search bar. So
Yeah.
as soon as you enter a search query, so in the background, you'll have a bunch of potential different websites that can be linked to this particular query. Okay.
Yes.
But you don't have to obviously attend to each of them. Each of them won't have equal priority, right? So you'll have some weightage given to all these links which can be linked to your query. Is it clear?
That are keys.
Yes, those are the keys. Now, what happens? You got the weightage value. Finally, you need the output, right? So, output is what you are giving all the links to your user with the associated weights. That is what the values multiplied with your softmax weights. The links which you're getting is the final output, right? That is the values, that is the words, but each of them multiplied with their associated priority.
Okay. Okay. You are saying that the softmax function is calculated, or the weights, final weights are calculated with the multiplication of values.
Yes. So if
Values with query.
not no, softmax is not calculated with the multiple attention value. If you look at the equation,
Yeah, attention value. Sorry. Attention value is calculated with all the values of
exactly softmax.
Okay, all the values of all the words with a particular query, not the key.
Attention is calculated finally with the softmax. Softmax is the priority, that is clear.
Yeah.
So what you do is value is nothing but all the input words multiplied with priority given when you're attending to a particular type of query. That's it.
Okay.
Just go back to the same analogy of your Google search. It will be at the end of the day, when you hit enter, you get a bunch of links. Each
Yeah.
of these links are values.
Yeah.
Each of these links are values. If you give numbers associated with each link, that will be your attention.
Okay. Okay.
Yeah. So we were in the forward function for the multi-head attention. So here we first create a key value. So here the key is nothing but you get the input query Q value. I'll show you how that input comes. So the key value we first resize into this particular shape, 32 cross 10 cross 8 cross 64. Similarly, query and value you resizes into the same shape. And now you multiply it with your vectors, W values. So these are all initial random key query values. So either it's random if it's the first, or it's from the previous ones basically. So you get self.key matrix, self.query matrix, and self.value matrix. All of them take input your corresponding key query value. Now you get your KQV matrices. Now these KQV matrices are reshaped into this particular dimension, 32 cross 8 cross 10 cross 64. Now this particular value is used in the bottom. Let's ignore masked for now. I'll tell you masked when we come to decoder, because that's where the mask attention comes into. So for right now, don't worry about the masks. And now this particular product which you're getting, right, which is nothing but the multiplication between the Q and the K adjusted value. So this is where you calculate your softmax, not softmax, first the dot product, and then after the dot product, the product is divided by the square root of the dimensions, right? which is root of 64, which is 8. Then this product is now, is there a question? Okay.
Your question means that mask attention that will be part of decoder, right?
Yes, yes. So I'll explain when the decoder will come. I'll explain why the mask will be used.
So encoder's job is to just encode this key value query key and values and the final output. That is just the encoding part it will do, right? That is the task encoder.
Yes, yes. Encoding at the end of the day, it will try to learn what are the good key and values, key and the value vector, value matrix.
Means what? I mean, good means relevant or what?
Yeah, relevant in, okay. So in the sense, like if I give a statement, right, input statement, and it will try to learn the best important features of those statement. Like the dog is sitting on the table. So when someone asks what is table's value, or what should it look like when you're looking at table, like what is it associated? Who's sitting on the table, right? The dog. So some kind of dependency or relations are being learned. That is what a good representation is basically.
Okay, so it actually tries to contextualize. I mean, the contextual information.
Exactly, exactly. So think again. One easy way when to imagine these is go back to your CNNs, right? How are CNNs learning representations? It looks at edges and then complex features on top of edges like circles and all those things. Same things you can think about representations here also. Some type of context information is being learned in that state.
Okay, and that will be encoded, and decoder's job is to uh, predict the next token.
Yes, decoder's job is to predict the next token based on your particular task, and that defines your loss function and everything.
Okay, got it.
So here we calculate. Here we calculate the scores f dot softmax. Now these scores are then multiplied with your value matrix to. We again write it in terms of scores only. Now these we concatenate all of them. Like I said, each of them 8 values will be there, right? Because from each head you get a score value. You concatenate all of them, and then you finally project them into the lower dimension using this out matrix, and that is your output of your multi-retention. So now once you get the output of the multi-retention, next steps is you have to go and do your layer normalization and residual connection, and then you also have a feed forward network, which again after that follow that we again do a normalization with a residual connection. So first steps is what we did till now. We went through the embedding layer and we got the positional encoding layer. Then we passed it to the multi-head attention in the second step and created some useful representations as output. Now, like I said, we have to create normalization and residual connection. How do we do that? With the help of the output from the multi-head attention. And then after that, we send it to the feed forward layer and again do the normalization and residual connection. So let's look now. This is the transformer block we are calling. Basically, it consists of one particular encoder block, this transformer block. So let's look at it. So as usual in the init function, we define certain variables. Normalization, we have layer normalization. I hope everyone knows the difference between layer normalization and batch normalization. Okay, so here we perform layer normalization, and we have two different layer normalizations because you're doing it for after the multi-head attention output and once you're doing after the feed forward network. Here we are calling the multi-head attention which we defined previously, right? Because the output of that is what is needed. Then we also create a sequence feed forward which is consisting of two linear layers. The dimensions are what, like again these are hyperparameters. You can decide how much you want the dimensions to expand and then contract. So here the embedding dimensions will be the input, and there's an expansion factor, how much you want to project it, and then you'll have to again decrease it and give the output as embed because this will go as input to the next next encoder block. So make sure. So I hope this idea of expansion and projection is that clear for you? Why do we do that? So imagine in CNN architectures also. I think it was in bottleneck mobile net architectures when we did this type of projection into higher space and then did some convolution and then we got back into lower space. So this people call it like something called as bottleneck layers, where you project it into higher space to get more, better features. But then you don't want to continue in that higher space because of computation. Then you immediately come back to the lower space after performing some calculation. So you can take some type of, you can get some idea of the same type of projection over here also. Then you have some dropout layers, which is the standard dropout, nothing new. Let's define the forward function itself. So first you get the output from your attention, multi attention, which is your attention out. Then you, like I said, we first do the residual connection, which is nothing but attention out plus your initial value, the which is going as an input to the multi attention itself. After that, you do your normalization, layer normalization, and followed by a dropout. Then this output is sent to the feed forward network, and then this feed forward output is again have has the residual connection with your previous input, which is norm1 underscore out, and then you perform another normalization and dropout. The simple. This is then followed out by the this is what you return. So this is simple. In encoder architecture, we combine all of them together basically. So like I said, you can define the number of layers you want in encoder block. So depending on the number of layers you define over here, that many times the for loop will run. And each time the layer is created, what is that layer? Layer is what the transformer block we just created, right? Which is combining your multi-attention, normalization, feed-forward network, and again normalization. Those four operations are created in the transformer block, and you just keep on calling them n number of times. So this is your encoder block. So let me pause. Any doubts in the encoder block and anything? Any other doubts?
I have a doubt that what are the hyperparameter in between the encoder block?
So you can look over here, right? Expansion factor is a hyperparameter. Number of layers is a hyperparameter. So, and apart from that, then I think dropout was also a hyperparameter. That's a very simple hyperparameter. Yeah, yeah, most of these you can also look into other values which you can create as hyperparameters. Yeah, I think mostly these are the important ones. I don't think others are there.
So I missed that part. Like you said, projection something. Like if a higher compute is required,
Yeah, right.
get that point.
So usually in convolutions, you remember there was an operation. I think when we performed mobile net architecture, there was a bottleneck operation where what you do is you first you have a normal input dimension space. You project it into higher dimension space just because you have this theory that things which are non-linear in lower dimensions, when projected into higher dimensions, become more and more linear. That's a normal idea. Like if you can imagine two things which are close by in 2D, when you project it into 3D, they become far away, right? So same idea. So when you're projecting something into higher spaces, the distance between classes or the features will get more and more. You can easily discriminate. So simple idea, they use that to project into higher space, perform a simple operation like convolution in that case, like a 3 by 3 convolution, and then you project it back downwards because you can't continue in higher dimension space because number of operations and computations will be more, because that high space is just for a immediate capture of necessary features, but you can't proceed in that space itself because number of operations will be very high.
Okay, so similarly here also,
Mhm.
I want to just analogically understand that. Like,
Yeah, so in here also, here I mean, see, I just gave an example. It's not necessary that you have to, that is what is happening over here also. It is similar because you have your lower dimension 512. Let's say expansion factor is 2. So you project it into some 1224 space. Then you do a simple ReLU calculations, identify all the patterns, non-linearity. And then you come back again from that 1024 space to a 512 space. So here there's not much of an operation happening. It's simple ReLU and weight matrix multiplication. In convolution, it made more sense because again, over there convolution is happening. That's why you can just draw an analogy. It's not that this is exactly like the bottleneck which we discussed in mobile net.
got it.
Yeah.
Even we have not used any type of activation function in these type of architecture.
No,
Why?
we just used, right, ReLU.
Okay, 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 okay.
So for calculation of the scores and all that, you don't need. The only where you had the linear layers are in this feed forward, and that's where you're using reloop. Okay, then let's go to the decoder one. So let's look again what are the steps in decoder. So now, as usual, the output first gets passed to its own embedding and positional encoding for the output also. But here we create a mask. Why the mask? Like we create a mask like this. So let's say I have this many number of input sequences, sentences which I have, and so these are all the words which I have. And if I put a mask on this one, right, it means that this particular okay, this is not, this is very clear. So if you put 1 comma 1 in the second row, if you look at it, yeah, is there a question?
No, no, no.
So if you put 1 and 1 in the second row, if you look, so it means that when you're processing the second element, you can only look at the first element. All the other elements are you should not look at, because these are all coming in the future, which the model didn't even predict yet. So that is why it is imperative that when you're training the model, use mask, because then it will make sure that it is only looking at the sentence words which have been predicted till now, that is the past left side. So that's why you create a triangular matrix, this where all the ones are on the left side for each column, not all the right side elements are zero. So I hope this idea of mask is clear. Is there any doubt in this? Okay, great. So
Size, we can define any mask size, or
that depends on your output number of words, right? So all of them have, this is training time, right? So output is known, ground truth, you know what is your ground truth, right? So you know the number of words in your ground truth. So all of these number of rows will be the number of words in your ground truth. The matrix should be of the square size, because you need that one to one mapping, right? So here if I'm saying one is on the first row, all of them in the future are not seen, so all of them will be zero for all the other words in the output input. Is that clear?
so mask size, what I want to understand is mask size means the number of words that we can mask at a time.
No, our mask size is basically the number of words you have in the output that is going as an input to the decoder. So if you look at it, so in this case, the outputs are the input to the decoder. Apart from the encoder outputs, there's another output which is a ground truth values, which will go as an input, right? So you have the number of words in this outputs. Like let's say it could be same 32 cross 10 words, like 32 input sentences, and each input sentence has 10 words. So the mask size will be then 320 comma 320.
Got it.
Yeah. Where do we use this mask? We use this mask after we calculate Q into K transpose. When after that we multiply this particular mask. We'll show it in the code where we multiply this particular mask. But it's done after the calculating the value of QK transpose before multiplying with your value matrix. Okay, after that, we also do the same residual connection and normalization. And then here, there is another multi-attention where we take the values from the encoder value. So here we call the encoder decoder multi-attention. So first multi-attention use mask multi-attention. Here the encoder values won't come. Then there's a second multi-attention where we take the encoder key and value matrices, and then you create the queries anyways coming from the output previous decoder layers, and then you use the key and value matrices from the encoder and calculate the encoder decoder multi-attention. So let's look at those step by step in the decoder block. So as usual, we'll use the same multi-attention. So let's look at where the mask is used now only. Multi-attention. Yeah. So here we provide the mask which we want. So if the mask is not none, we just create a mask. Which is basically the triangular matrix which we create, but most of the times it's good if you give your mask. It's nothing but a simple triangle matrix, right? Worst to worst, what you have to do, you have to just create once for all the times which in the future the word should not be seen. That's the most simplest mask you can create, but there is a lot of other types of masks also which you can create based on your task. So depending on your task, people have created different types of masks. So this product is that so product is multiplied with that particular masks, and then before sending it to the dividing it with the square root. So you first calculate q into k transpose, then you multiply it with the masks or identify where. What I mean by multiplying is basically look at those positions which are ones, ignore all the positions which are zeros. In this case they don't ignore it, in this case you multiply it a very small number, so automatically when you do softmax those will get ignored. So obviously in to make things simple, that's why we write this. Wherever the mask is 0, you put the value as e. This value is very small, it is minus 1 to the power 20. So it is like minus 0.00001, very small number. In the softmax this will automatically become 0, so it won't add any value, it won't add any priority when you're multiplying with the value matrix. So this mass multiplication is clear, right? Any doubt in this?
Yes.
No.
So decoder. Yeah. So first decoder block, we again have the same multi-layer attention, norm layer, dropout layer, and the same transformer block. So this transformer block was defined previously, right? When we are defining the encoder block which we defined. This is the transformer block. What did the transformer block contain? It contained its own multi-layer attention, norm layers, and the sequential layers. So we are calling an instance of that particular transformer block. Okay. What is the forward function? The forward function says that first send it to the attention, then do the residual connection, and then send it into the transformer block for the multi-head attention and again certain residual connections. So in the transformer decoder, what the same, you create a decoder block, and this decoder block you repeat it n number of times depending on your particular n value, right? How many layers you want in decoder, you just repeat it. So again you have your same word embeddings, positional embeddings. These are all for the output values, not for the input values. So you first send it to your word embeddings, then the positional embeddings, and then you define a mask. That mask is sent as an input to this particular function. That particular mask is now used in your decoder block. So once you understand the encoder block, only difference in decoder block is having that particular mask. Most of the functions, all of the functions in fact, follow the same which we use the encoder block. Only the extra value is this particular attention, which this attention block which we create, which takes the input from the output. Sorry, that is very confusing, which takes the input from the values which are provided to the decoder layer. Okay. So I think once if you understand this, then transformer is just now you create the class transformer, you create two different variables, transformer encoder, transformer decoder. Here you make your target mask. Like I said, a simple mask is you create your triangular matrix filled with ones. Then decode function is created for the inference part. Will come to that during the inference. And this is your forward function where you first make your target mask. You first send the data to the encoder, get the encoder output, then send it to the decoder along with your target mask. That's it. And this is your final transformers architecture, which will return the outputs, which is your predictions. It's a token by token predictions basically. And now with this help of predictions, you can either train with any cross entropy loss and everything. So training a attention transform model is quite expensive. So in our case, we just use for testing, because training takes a lot of time and it's very compute intensive also. So let's look at how we are testing. Imagine let's say we have the simple source and target. So these are the different tokens, 0 to be the start of the token and 1 to be the end of the token, and these are a bunch of different other token values. So they're not following, I mean, they're not representative of anything. It's just a bunch of different token numbers, you can say. Then here you call the transformer model which you created, instance of it. If you print it, you will see all the layers which you created. Sorry.
Sorry, can you just go back to that input and output?
Yeah.
That so I
So
didn't.
this is just a test. This is just a test example. These are not like actual. This is just like dummy test example. Just
So
to show the
considering that we have already converted our text into this
numbers. Yes, yes, yes.
What is the target?
Target is the bottom. That is also again some dummy.
So it is dummy, but it is initialized to some values, and then whatever output I will get through decoder, uh, that should be the target value, is it?
Yes, that should be the target value. Whatever after the decoder predicts, right, that should be closer to the target values.
Okay.
Yeah.
But in practice, how do you convert that? I mean,
Tokenizers. So there is something, yeah, there's something called as tokenizers, which converts your text into tokens, gives you the token IDs also basically. Those token IDs are then converted into embeddings.
embeddings means this tors.tensors values. In this case,
No, embeddings is the nn.embeddings which we created first class, right?
okay.
Yeah, so tokens is what you see the numbers 0 to 5. These are the token IDs. So every word is converted into these tokens. You can again use a standard tokenizer, or each LLM has its own tokenizer, because uh, tokens, while for us you can say each word to be token, that's not the case. Sometimes half of the word is also considered a token. Some people have special characters as tokens in their vocabulary. So when I say people, some models basically. So it depends on which model you're using, what type of tokenizer you want to use. So each of the tokenizer converts your text into numbers, which is token IDs. And if you send, that is what we are sending as input. In the input, when you send, if you remember, we did embedding, right, in the start. Those will convert these numbers into the vectors.
Even I have read somewhere that even the sentences are also the tokens.
Yes, could be. So there are a lot of literature available on tokenizers. I'm not an expert in that field, but yeah, there is very likely that sentences could also be tokens. So I think Swati, is that clear?
Yes, yes. But only the thing, the target, I think, when you'll be showing the decoder output and how this target tensor is updated, that's where I need to check that once.
Yeah, so here we are not updating the target tensor. We don't update target tensor. Target tensor is ground truth, right? So if it's like image classification, right? If you have a label of a cat, you don't update the label of the cat. You just
Got it.
get the predicted value and you compare it for accuracy or whatever metric you want to use.
Hmm. But since these are dummy, the loss values, we can't assure that.
Yeah. So here we're not training also. Here the obviously inference also will not be great because it's just a dummy value. We just want to make the pipeline once, and once you get the compute resource, you can train it on data sets, big data sets.
Got it.
Yeah.
Thank you.
The training pipeline remains the same as we discussed till now, right? For all the other models, the pipeline remains the same for each epoch, and inside that also for each mini batch. That will remain the standard values. You just will get tokens instead of images. You'll get something like numbers basically now. Images can also be done. That's, it's not like images can't be done for transformers. That also can be done. Yeah, so this is what that simple prediction is. So you predict the following shape 2, 12, 11. This is again we are doing it for another particular source and target. Here we are predicting 1, 1 as the output size. So 0, 12 as the output size, because the vocabulary size itself is 12, and out of all these you pick one of the values, which is the softmax. Obviously these are bad values for now, which is clearly nothing. So these are all the sources which I wanted you guys to go ahead and look. The first two sources, right? Very good sources, because they actually help you understand much more clear with all graphics. So whatever I explained today, every step they have an image with it. They explain step by step images and all. So you can look at those images, get more intuitive understandings. Both these links are very good. And if you want to look at the PyTorch implementation, you can also look at this YouTube video. So yeah, that's what I wanted to discuss for today's class. I know it was a lot of confusion in the code, but it's good if you understand at least 60% from the class, and maybe please try it out once on your own time. Unless you do that, you won't understand transformers, because it's easy to get confused if you don't practice with transformers. So yeah, any other questions? Anything else that is unclear, we can discuss right now.
But in practice, we will not write this transformer from scratch, right? We will be leveraging the pre-trained
Yes. So most of the times you will be leveraging, but it's good to have an idea, especially if you want to change few layers or make it more customizable, or fine tune it for certain layers and all. it's definitely good to have an idea how the
Yeah,
architecture
that
is.
is true. Yes,
Yeah.
conceptual.
In fact, I would suggest write it on your own 1-2 times so that you'll get a better understanding. Because it's not as simple as CNNs, right? As you can see, CNNs is much more simpler.
In the whole, we can say that to understand the architecture of transformer, we have to implement by ourselves.
Yes, so at least once if you implement by yourself, right, you'll get better idea. You'll understand much more steps clearly.
So can we consider this as the vanilla transformer and try to refute it?
Yes, so this is actually the transformer which was used in Attention Is All You Need People, which was the first transformer, in fact. So based after that, people just kept on modifying with a bunch of different things.
Okay, so this is the vanilla transformer.
Yes, you can start from here. Yeah. Okay, then if there are no questions, then we can. Is there a question?
No.
Yeah. Okay. Thank you.